Welcome to the Space Telescope Public Lecture Series. Tonight's talk, Armchair Astrophysics Volume 2 by Quyen Hart of the Space Telescope Science Institute. I'm your host, Dr. Frank Summers of the Office of Public Outreach, and I would like to thank our wonderful tech team, Thomas Marufu and Grant Justice, who help bring this to you every month. I will also note that we will continue to be online only until further notice. Most likely we will be online only throughout the rest of 2021 and into the beginning of 2022. Whoops. Our upcoming talks. In August, we will have the importance of small objects, exocomets, not exoplanets, but exocomets, comets around other stars, by Isabel Rebolito of the Space Telescope Science Institute. On September 7th, we will have recipes for planet formation by Nicole Arulanthanam, also of the Space Telescope Science Institute. And in October, we have a special guest, Todd Lauer from the National Optical Astronomy Observatory, and he will talk about a really interesting paper that they put out earlier this year. How dark is space? What is the true blackness of the night? And if you would like to find out about what these upcoming lectures or more information, you go to our website, stsci.edu/public-lectures, or you go to your favorite search engine and put in Hubble Public Lectures, and you should be able to find this page. On the lower left, you can see the links to our webcasts, both on the YouTube playlist and on the STSCI webcast archive. On the lower right, you can see how you can subscribe to our email list. Just enter your email address, push that button, and you'll be subscribed to our email list. We also, on our website, we have the information about the upcoming lectures, the list of them. But if you click on each one of them, they show you the details, the description, and after it's been recorded, the links to the STSCI webcast, as well as the YouTube webcast. For the email announcements, as I said, the easiest way to do it is just to sign up at our website. You also may want to subscribe to our YouTube channel, youtube.com/Hubble Space Telescope. You will, if you subscribe, you will get notices of our new videos as well as reminders of live events. And finally, if you have comments or questions, you can send them to the email address publiclecture@stsci.edu. Our social media channels are available for the Hubble Space Telescope, the James Webb Space Telescope, and for the Space Telescope Science Institute. And you can see them listed here for Facebook, Twitter, YouTube, and Instagram. If you would like to see what I have to say about the universe, well, I do a tiny bit of social media, and you can find me on Facebook and Twitter at Dr. Frank Summers. And now our news from the universe for July 2021. Our first story is about Hubble and the extended anomaly that's currently happening with Hubble. So if you didn't know, on June 13th, 2021, Hubble entered what we call safe mode. It's not taking any observations. Everything's all in safe mode while we diagnose the problem. The problem is involved in the Science Instrument Command and Data Handling Unit, the SIC and DH. And it is an issue with the payload computer. On June 13th, the payload computer stopped. And on June 14th, they tried to restart it, and that restart failed. It initially indicated that there was a degrading memory module. There was problems reading and writing to memory, but there were unsuccessful attempts to switch up to a backup memory module. There are 4 memory modules on Hubble. Only one is active at a time. And so perhaps the memory errors were only a symptom. So they moved on to other hardware tests, the standard interface and the central processing module. These did not uncover the problem with the computer. So there is redundancy on Hubble. There, as I said, there are 4 memory modules, only one of them is active, but there's also a full backup payload computer. So they switched to the backup payload computer. They tested out different memory modules. They did various configurations of the main computer and the backup computer and the memory modules, and they still kept getting the same errors. So after all that testing, they've now moved on to looking at other hardware, the command unit science data formatter, the wonderful CUSDF, got to have the acronyms for these, as well as looking at the power regulator in a power control unit. They are looking at switching to the backups of those, but that's a little bit more complicated. So at this point, we do not have the solution for what is wrong with Hubble. We have not isolated the problem to a specific piece of hardware, but they are still working at it. Now, I will note that things like this happen relatively regularly, okay? We have one or two safe mode events every year. Matter of fact, one of the most important ones happened in September 2008. And this is a gorgeous picture of the space shuttles at the launch pads getting ready for servicing mission 4 in September 2008. And that was when the CU-SDF failed. The CU-SDF failed at that point, and we had to switch to a backup. Well, this is such an important piece of equipment that we actually delayed servicing mission 4 for another 6 months so that they could add the replacement of the SIC and DH to servicing mission 4. So the SIC and DH was fully replaced during servicing mission 4, which kind of looks like a smart thing right now, considering that it is having problems again here in 2021. So there is a backup for the CU-SDF, which if they hadn't replaced it in 2009, there wouldn't be. So we have really amazing people working on this. They have solved all these problems, but they have to work extremely slowly. They have to work very carefully and make sure that they isolate it to what piece of hardware is not working and make sure they confirm that all the other pieces of hardware are working. So they're still working the problem. Our second story tonight, separated at birth, the lunar edition. Now, what we're talking about here involves the Juno mission at Jupiter. Juno is a mission to study the magnetic fields and the atmosphere of Jupiter, really trying to understand the internal structure of Jupiter. But one thing that they did is they put on an instrument called JunoCam, which is not a science instrument. It's really an outreach camera to take gorgeous pictures of Jupiter. And it really has found some gorgeous pictures. Like this, getting really close to Jupiter's atmosphere, got an amazing picture of this storm on Jupiter a couple years ago. And also, it has taken long shots and being able to get Jupiter and the 4 Galilean moons of Jupiter in the same shot, Ganymede, Io, Callisto, and Europa. They have since been able to configure the orbits to fly past some of these moons. And this month, they flew past Ganymede. And so they got the closest approach to Ganymede since the Voyager missions in the late 70s and early 80s. So, brand new picture of Ganymede. And this is taken from 1,000 kilometers away, like 650 miles above the surface, okay? Really cool. Now, it's in black and white because it's just the green filter. They took red, green, and blue filters, but they wanted to get the picture out really quickly, so they just released the green filter. And when I looked at it, I said, wow, that's really great, because I mean, this is just a tremendously detailed image of Ganymede. But I also said, you know, I think I've sort of seen this before. And doesn't it sort of look like our moon? Yeah, it kind of blink back and forth. Well, let's see, there's Ganymede and there's our moon. Were they separated at birth? The answer is, of course, no. They were not separated at birth, okay? Ganymede formed in the outer solar system. The moon formed in the inner solar system. Ganymede has this huge icy layers on its surface. The moon is all just rock, okay? But they do look similar because they've undergone the same processes. So, for example, down here, you can see this giant crater with rays extending out on both of the objects. If you look in the upper right, you can see these smooth patches. On the moon, this has happened when punctures of the moon and lava welled up and flowed out. On Ganymede, I would expect that it would be punctures that flood water to spread out and create these smooth, clean patches. There are also these rugged patches where tons and tons of craters have formed. So while the moon's surface is rock and Ganymede's surface is ice, they have undergone the same processes, mainly cratering, small, medium, large cratering over billions of years, and end up looking the same. So this is just a preliminary image. As I said, it's just the green filter. We're looking forward to getting all the red and blue filters, add to it to get the full color image from it. But it shows you what Juno can do because of its location and able to fly up close and get personal with these moons in the Jupiter system. All right, our speaker tonight is Quyen Hart. And Quyen has been with us at the Space Telescope Science Institute for a little over 2 years, or it's 2 years in September, almost 2 years. She comes to us from a great history of doing lots of astronomy and other things in various places. She did her undergraduate work at Villanova and her graduate work at the University of Colorado, Boulder. She spent some time at the Scripps Institute studying atmospheric science, and then she went on to be an associate professor at Regis University, where she trained in teaching classes and such. She tells me that while she was at Scripps Institute, what was a fun thing to do was at the end of the day, Scripps is right on the ocean. You can look out over the ocean, looking west, watching the sunset. And that they would go out in the evenings and look for the fabled green flash. Now, I will tell you, I have never seen the green flash. I haven't spent the time looking for it, but Quyen tells us that they were able to see the green flash many times, so she is an official member of the Green Flash Searchers Club. Ladies and gentlemen, Dr. Quyen Hart.
Thank you, Frank. Welcome everybody to tonight's public lecture series, where I will continue a talk with you all with the title Armchair Astrophysics Volume 2. So I hope this will be an annual event that you all look forward to. Whoops. So last time we were thinking, I wanted to talk to everybody about astrophysics in a nutshell, because I really think and believe that anyone can talk about science, talk about astrophysics with people around you. It's all how you see the connections in what you're learning about in astronomy, what interests you and what interests the people around you. And you have all of this background knowledge so that you can take that information and really crack that nutshell by using that information. You use your everyday experiences that you have and use it to crack that science nutshell of astrophysics so that you can sit down at a comfy location and talk to people about what interests you in a way that is very understandable to you and to the people around you. So when we think about physics, as a reminder, it really is the study of matter, of motion, of forces and energy. So these are words that you are very familiar with in some way. Okay, motion being movement, like on a roller coaster for summer fun, or if you enjoy playing a game of billiards here. Light, you see rainbows, light coming in through windows, campfires, electricity, light bulbs, colors, reflecting, emitting. These are all things that you're familiar with. Now, what is astrophysics? It's all of those things, except we focus the study of those pieces in space. So we can look at different objects in space, study them, and try to understand how they came to be. So in tonight's talk, we're going to look at some everyday phenomenon that can help you to understand how we understand other things in space at a beginning level, and then just building up a little bit more intuition for that. So let's start with our first one here. How do we gauge distances? Are things nearby or are they far away? So for example, on the left side images here, we have some images, of a field of flowers, some clouds, and some distant objects. And you use your everyday experiences to gauge, the flowers are probably close by. These distant trees, they're distant. They're smaller than I'm used to seeing if it's right in front of me, so they're further away. And these clouds, maybe some of them are close by, but it's really hard to tell because I don't have a good sense of the sizes of clouds. Now, if you look at this mountain picture, you're also using some of that same intuition. You know how big you think mountains might be. You see trees, some of them look bigger, they're probably closer. Some of them are further away, they look smaller. So that kind of intuition is there. But as soon as you get to astronomy and look out into space, the intuition kind of might fall through the cracks a little bit. So for example, in this image here on the upper right-hand side, it's a field of stars. Are they close by, some of them? Are they farther away? Are they all at the same distance? It's really hard to tell. The image in the lower right-hand side, are those stars? Are they galaxies? Are they nearby? Are they far away? So it's really hard to gauge distances just by looking at astronomy. We need some type of method to figure out distances to the nearby things. And then based on that, we can start to look at distances at things a little bit further away, and then a little bit further away, and a little bit further away. So distances are actually extremely hard in astronomy, and we have to build on our knowledge of nearby things to get to objects that are billions of light years away. So let's start by looking at an example. So if you're in your car driving, traveling around in the summertime, you notice that if you look outside your window, you'll see the trees moving by quickly. But the mountains don't look like they're moving by very much, but they're moving a little bit. They appear to move. And the distant, say the clouds, perhaps you might have here that's saying, oh, the clouds are following me. But they're really far away sometimes and you're not sure, or if the sun feels like it's following you. Okay. So we have this, this idea of if I'm moving and changing my perception, my angle out the window, where I see things in that field of view in this window changes with time. And how it changes allows me to gauge something about distance. Okay. Let's see, I think this is the same video here again. Go to the next one. So I want to do a little hands-on activity with you all. So this just happens to be Eta Carina in different colors of light, but I'm going to put 3 stars, artificial ones, on the screen. They're just 3 different sizes. You get to pick which one you like. So what I want you to do is I want you to hold your hand out at arm's length, okay? And just hold up your index finger. I'm sorry, I can't see my screen here. Let me see so I can see what I'm doing so I don't block. Okay. So you hold your finger out at arm's length here, and I want you to cover up, pick a star where your whole finger covers up that star, okay? And notice I'm covering my one eye. So I want to look out at it with your right eye. So I'm covering my left eye, holding my finger out at arm's length, and I'm covering one of the stars. So right now I'm covering up the middle star. Then I'm going to switch my hand and look at it with my other eye. Okay. So what you should see is it looks like your finger is moving, but your finger's not moving. Really what's happening is that your line of sight to your finger, one eye versus the other eye, compared to the background of Eta Carina, is making it look like your finger is moving. Okay, so let's try this again. So you're covering up your star that you've chosen, and you're looking at it with different eyes, and you see like it moves. Now pull your finger closer to your face and do the same thing again. Okay, what do you notice that's different now that your finger is a little bit closer to your face? You'll notice that your finger appears to move more than it did before. The position of your eyes have not changed, but the position of your finger, which is closer to your face, has. And as you look at it from 2 different locations, it looks like the finger shifts more. This is called parallax. And notice that it had to do with 2 different locations, in this case, one eye versus the other, and the location of my finger relative to Eta Carina, which is a background object that was stationary, stationary for the most part. Okay, so we can do the same thing in space. So in space, we're sitting on the Earth that orbits the sun. So we have we have many unique vantage points, but we have 2 very unique vantage points. We have the Earth at one location here. 6 months later, it's at another location over here. So that's like 2 sides of your eyeball when you're on either side of Earth's orbit. So if you see a nearby star here, which is like your finger in the previous example, it will appear to shift in the sky relative to the background stars. And then the case in the example before, the background stars was the image of just random image of Eta Carina. So let me just go back a little bit here and try it again so you can see. So if I could move my eyes, one eye from left to right, you would see the motion of the star change over time. This is a different view. It's a top-down view. So in December, I look at some star. In June, I see the star again. Notice the star hasn't changed. The background stars haven't changed. Only I have changed my location. And the movement of the star in the sky is called the parallax angle. And it's directly related to how far away the star is and how far away we are when we are moving in our orbit around the sun. And that is a geometrical relationship that we can use trigonometry, very basic trigonometry, to get a direct measurement of the distance to that star if I can measure the parallax angle. And that's really, really amazing. You just need extremely sensitive telescopes that can measure the position accurately enough so that you can see this shift in the sky to see the parallax. Because once you see the parallax that changes over the course of year to year to year, then you can get the distances to nearby stars. So to gauge these distances, a current telescope doing very precise measurements of positions as well as brightness and spectroscopy is Gaia. It's called the Global Astrometric Interferometer for Astrophysics. It's a European Space Agency astronomical observing mission. It was launched in 2013, and one of its goals here is to look at the positions and brightnesses of stars in our galaxy and look for calculate their distances by parallax, but also look for their true motion through space. Now you can see how it gets a little complicated because a star might look like it's moving because of us moving around the sun as the Earth orbits around the sun, but there's also true motion of the stars through space. So we have to know, have very accurate measurements for that. So over the course of this mission's lifetime, it'll be able to measure about 1 billion stars to really get a map of the stars in the Milky Way and then start to understand the evolution of the Milky Way. So in the past, the prior mission that did another really nice mission to measure parallaxes was called Hipparchus, also an ESA telescope. And that telescope could only measure distances a little bit beyond the orbit of the sun, not far, about 300 light years or so. Now Gaia here can measure the accuracy of stars to within 10% out to about 30,000 light years. Okay, so this bigger circle. So this is a big leap from Hipparchus, but it's not quite that large when you think about the diameter of the Milky Way. The diameter of the Milky Way is on the order of about 100,000 light years. So this is getting out to about the center of the Milky Way. But some other stars a little bit further out with a little bit less precision will be able to, they'll be able to also measure. But the point is that more stars and their positions are being able to be measured as well as their brightnesses so that we can start to see, okay, fast forward here to some of the positions. So if you look at this video here, you can see this is from some of the data from Gaia, and you can see the motion of the stars, the apparent motion due to the Earth orbiting around the sun. And so you could see that cyclical kind of wobbling back and forth, just like your finger seemed like it was moving back and forth. So the distances to all these stars can be measured as a result of that shifting. Now, once you take out the shifting, you can start to study the true motion of the stars through space. And so this is a forward modeling of the true motion of those stars over time. And what you saw there, which I'll just rewind a little bit here, is that this is the constellation of Ursa Major. And over time, the stars in Ursa Major, which are very distances from the Earth, will move, and the constellations, as we know it now, will be morphed because of that true motion. Okay, so that was just distances. How do you gauge distances? Use parallax. So now let's talk about another everyday experience that you might have, which is going around and around in circles. Now you can take that as a literal saying or figurative one. So since it's summertime here in the Northern Hemisphere, you could talk about going around on a carousel, going on a Ferris wheel that has motion in a circle. It's hot. You might have a ceiling fan on or a regular standing fan where the blades are spinning. Many of us are on computers a lot these days, and sometimes you hear that fan spiraling all around in your laptop. So something's spinning in there, okay? A few years ago, these were kid favorites. They're little fidget spinners, and they could spin quite fast, so they're spinning motion. And then of course, we have the rotation of the Earth, which is also spinning motion here. And this is from the Discover satellite looking down. And we also have objects that orbit around the Earth too. So in some ways, that's a spinning motion. It's an orbit, it's still motion in a circle. So let's talk about motion in a circle. So for example, I'm going to use the ceiling fan as our everyday example here. So a typical ceiling fan here is about 42 inches in diameter, about 1.3 meters, and it rotates at about 100 rotations per minute, RPMs, okay? So as the blades spin round and round, you might ask, well, how fast are the tips of those blades moving? Well, let's first think, well, if I have 100 RPMs, there's 100 rotations per minute. How many rotations do I get per second? And that works out to be 1.7 rotations per second. Okay, so if I have a stopwatch, I can count almost 2 rotations in a second, but not quite. So what I really want to know is how long does it take the blade to go around one time? So if I were to take one point on the blade and watch it go around one time, how long would that take? So 100 RPMs is roughly 0.6 seconds for one tip of the blade to make one circle around here. So as an analogy, if we talk about the Earth rotating on its axis, it takes 24 hours to complete one rotation there. So that's the period of the rotation, 24 hours. Yeah. And that period, of course, we call it a day here, an Earth day, that is. So again, we wanted to know how fast are the blade tips moving. Now, speed is a very simple concept. It's the distance traveled in a given period of time, in a given time interval. So for example, if you look at your speedometer on your car, you might be going at 65 miles per hour or 90 kilometers per hour. That's how far you go in 1 hour. It's your speed. Now, for this circular motion of the fan, if I look at a dot here, the dot would make a path that's marked by this dotted line here. Okay, so that distance traveled is really the circumference of a circle with a radius that's from the top of the blade here to the center of where it rotates, which is 2 pi r. Okay, so a 1.3 meter diameter ceiling fan, half of that is the radius, so 0.66 meters. So the circumference is 2 pi times 0.66 meters. So multiply that all together, and I get a distance from this point going around the circle once of about 4 meters, 4.1 meters. Okay, great. I know the distance that it will travel in that circular motion. So now I can answer the question of how fast are the blade tips moving? Because remember, speed is just distance for a given time interval. So we already know that it rotates 100 times per minute, which is 0.6 seconds for once to go around. That's the time. And the distance we just calculated, which was the circumference. So 4.1 meters divided by 0.6 seconds is 6.8 meters per second. That's the speed, which in miles per hour is about 15 miles an hour. So a rough gauge here, I'd always tell people, you know, numbers don't mean anything if you don't have a reference point. So this is a typical biking speed if you're not, you know, running, you know, not in a race or anything like that. So 15 miles per hour, that's reasonable. I know that I won't get hurt if I somehow accidentally get in touch with, I have a ceiling fan right here. So 15 miles per hour, there are limits, you know, safety limits for ceiling fans, obviously. So this idea of speed is distance over time is going to be really straightforward for us to use in other astronomical scenarios. So we needed to know some type of distance traveled in that circle. But that circle, we need to know something about how far away. In this case, I needed to know the radius of the ceiling fan here. You might want to know the speed, which is how fast it's moving. And you want to need to know how much time is involved in order to rotate once. So the great thing here is that we have 3 terms. We have speed, distance, and time. And if you have 2 of those, you can always figure out the other one. So it's a nice mathematical solution here. Equation with 3 numbers. If I have 2, I always can get the other one. So what we're going to do here is, well, let's figure out how fast or how much, let's take the Earth as an example here. So again, we have the rotation of the Earth, and let's say that we live at the equator, and you want to know how fast am I moving when I'm on the equator just because the Earth is rotating. So in order to do that, we can answer how far we are from the center of the motion? Okay, we can. The distance to the center of the Earth here. How fast does the Earth's surface rotate? Well, that's what we're trying to find, right? And how much time does it take to rotate once in its orbit? Or on its axis? We know that it takes 24 hours to go once on its axis. So we could fill in these numbers. The radius of the Earth here has actually been known for some time. So that wasn't an unknown here. It's 6,378 kilometers, which is approximately, I'm rounding up here, about 4,000 miles, okay? So the circumference around the equator here is about 40,000 kilometers, okay? And again, it takes us 24 hours to complete that rotation around once on our axis. So that means I can calculate the speed. So the speed here is the distance over time. So that's the 40,000 kilometers divided by the 24 hours. It comes up to 1,666 kilometers per hour. Okay, so now you know that compared to typical car motion. In miles per hour, it's 1,038 miles per hour. So it's quite quick if you're just sitting on the equator and moving with the Earth's rotation. Now, if you're at higher latitudes, your speed on the Earth as it rotates is a little bit smaller because the circumference at that latitude is smaller. Okay, but you still make a rotation in 24 hours. So you're going smaller distance in the same amount of time, so you can go slower. Okay, so that if you're sitting right at the North Pole here, you're not rotating at all because you're standing on the top of the world. Okay, so this is using the same concepts as we did for the ceiling fan to understand how quickly the tips of the ceiling fan blades were moving to get the rotation at the surface of the Earth here. Okay, let's take it one step further. How about the sun? Okay, so same equation. Speed is distance over time. I have 3 numbers. If I only have 2, I can calculate the third. Okay, so we have the question of how far away, how fast, and how much time. All right, well, let's start with how far away. So the sun is a star in our Milky Way galaxy that contains hundreds of billions of stars. And early in astronomy, astronomers thought the sun was at the center of the galaxy. It was really hard to figure that out. But when they astronomers started to tease out different components of the Milky Way, they were able to see that there was some distribution around the center, these specifically globular clusters. And once they were able to map out the distances of those globular clusters, they can map out the distance of the sun relative to the center of that distribution. And it's roughly about 26,000 light years away from the center of the Milky Way galaxy. So that's roughly, that's the distance away from the center. So if the galaxy is rotating, then their circumference, which is the path in the dotted orange circle there, would be about 163,000 light years. Okay, so that would be the distance traveled. All right, what other thing do I know? How fast? Okay, how fast is the sun moving through space? Now, you can make accurate measurements of the positions of stars nearby, but you can also measure the speeds at which the stars are moving through space, looking at spectroscopy of those stars. That's when we take light and we break it up into very, very detailed pieces of the light, looking for signatures that are like fingerprints of the gases. And that actually can give us motion. It's very similar to the Doppler effect that you can use on radars to get a sense of speed. So astronomers can do a similar thing. And once you know what the motion of stars are around the sun, you can start to figure out how fast the sun is moving as well. And we find that the sun is moving about 240,000 kilometers per second, which is roughly 86,400 kilometers per hour, which is about 537,000 miles per hour. So it's really fast. Okay. So we have 2 of the 3. We've got distance and we've got speed. So that means now I can figure out how long it takes the sun to go around galaxy once. Okay, so time here, if I rearrange that, is just the distance divided by the speed. So if I take that distance and by the speed, it takes the sun about 200 million years to go around one time. Okay, so these are really rough approximations given assumptions like circular orbits. That's the main assumption here. So that's 200 million years to go around one time. Now, if it takes the sun that amount of time to go around once, how many times has it gone around the Milky Way? Well, the age of the sun is about 4.6 billion years. So it's been going around and around the center of the Milky Way about 20, just a little over 20 times here. Okay, so again, everyday concept of circular motion, things that you see in your space around you, outside, everywhere, can be used to do very simple estimates for other types of circular motion in space. So now let's talk about energy. Okay, so I just want you to take a second and look all around you. Look in the space where you might be. You might be in a coffee shop, you might be outside enjoying the weather, you might be inside with your family, and look around. Maybe your space is clean, maybe it's not so clean. It's perfect for you. Is there anything interesting in that space? What if you look outside? What's interesting there? And, so let's see what kind of energy we can talk about. Now, energy is a word that we use in science one way, and we use it very informally in everyday speak. So I wanted to kind of draw some definitions so we can use that as a common language here. So there's all different kinds of energy, first of all. And let's just talk about energy due to motion. We call that kinetic energy. So anytime there's movement, anytime there's speed, physically go from one location to another, be it small or big, there's going to be kinetic energy associated with that motion. So if you're running down the street, moving in your car, on the surface of the earth, rotating around, or on the earth going around the sun, or the sun moving through space, those ceiling fans, the air in this room that I'm sitting in the room that you're sitting in, it's moving as well. So there's kinetic energy all associated with motion here. Now, temperature, you might say, well, is temperature energy? What? She's bringing up temperature for some reason. Okay, let's step back for a second. So temperature, we talk about things that are hot, that are cold, that are warm, and astronomers talk about the temperature of different objects in space, and that could be very relative. Someone's hot might be someone's cold. So we could talk about things that are hot, like lava, or the hot air on a summer day, or it could be very cold, like the ice cubes in your freezer, or the cold air outside when it's snowing. What's warm? It's relative. Maybe you're really hungry and you love warm biscuits. Maybe spring is warm because you're trying to grow things and you're really ready to get out of the cold. So what's warm, right? So, but we talk about these as a description, and notice that they're all pictures of big things, macroscopic things. But what happens if I look at it from a microscopic standpoint? So in this image here on the left, I talked about how the molecules in the room here are moving. They're not static. They don't stay still. They're moving all around. They bounce into each other. They hit the walls. They hit your skin. And what you feel as temperature really is a bombardment of those molecules with your skin, transferring some of that kinetic energy to your skin. Okay, and your skin warms up because you get some energy that's transferred there. So that's what's happening with gaseous molecules. And when we try to say something about the temperature, when we talk about liquids, we could have a cold liquid or a warm liquid, like cold water, warm water. So the molecules are still, they can affect each other, but in cold water, they're more closely, they're closer to each other, where the warm water, they're a little bit further apart from each other. So the temperature has to do with how for lack of a better word here, fluid the liquid is, being a little bit closer versus less separated here. Now a solid, we can think of a solid, when you think of solid, knock on the table or the chair, it's, it's solid, but that's what we say when it's solid, right? So we're talking about something where the pieces are not, can't move around very much, but they can still vibrate, okay? And there's usually a crystalline structure sometimes with the way the material is laid together. But they can still move. There's still kinetic energy associated with a solid, because we know things that are solid can have a temperature to them. And so it's relating to the jiggling, the jostling of those molecules in the structure of that solid material. So that's kinetic energy. And oh, let me go back one. So temperature at the heart is really kinetic energy. It's energy due to motion. So the hotter a gas is, the more quickly the particles are moving. Same thing with liquid. And with a solid, the hotter it is, the more jostling it is. The colder it is, the less jostling, less movement. So there's an absolute zero on the temperature scale where you can say that motion ceases because there's no kinetic energy, zero temperature. Okay. Now that's just one kind of energy. There is also different kinds of energy. So there's potential energy, and potential energy is stored energy that can be converted to all other types. So for example, the fruit hanging on this apple tree, they all have kinetic energy. So just like this little, you can't see it, little apple I have here. So right now it's hanging out. Oh, this is not the best here because of the green screen. That's good. So this apple here is at a certain height above the surface of the earth. But you know that if I let go of this, it's going to start moving, right? So I dropped it and it moved. As soon as it moved, it had kinetic energy. So they can be converted. So that gravitational potential energy was converted in that case. Now the fruit has complex minerals and molecules too. They have chemical potential energy in the bonds. There's one molecule called lutein here, which has 40 carbon atoms, 56 hydrogen atoms, and 2 oxygen atoms. And this is one of many molecules and minerals in the atom. And those elements are bound together in that molecule with chemical bonds. So if you break them apart, it requires energy, but it can also release energy too. And then when we look at the actual elements themselves, we have a nucleus and electrons. And those have blinding energy that's also, it's another type of potential energy. So in your room here, where you're looking around, so now look around. Now you can start to spot different types of energy. So maybe you have something on a shelf that's high up that has gravitational potential energy, has the ability to fall off and change into motion, right? You have food around your house. There's lots of chemical potential energy stored there. Anything with mass has energy too. So you might be familiar with E equals mc squared. Anything that has mass has energy. It's called mass energy, but it's really hard to get to. But it's there and has the potential to be converted. And this is how stars make energy by nuclear fusion. Because you can turn 4 hydrogen atoms into 1 helium atom. And there's a mass difference between that. And that mass got converted into energy. So that's one way of transformation of one type to another. There's other types of potential energy too. There's electrical potential energy. Your body is one basically big electrical circuit, sending electrical signals from your brain to your different parts of your body to make your hands move. If you're walking, you have elastic potential energy in your muscles as they contract and release. Springs in your cars help to absorb some of the jostling. So there's lots of potential energy around. So each of you has loads of potential energy of all different kinds. Even the astronauts up in the International Space Station have different kinds of energy as part of their everyday life here. Okay. Now, another type of energy is radiative energy, and this is the energy carried by light. Okay, so sunlight that you see in visible light with your eyes here and starlight are just one type form of radiative energy in the visible. Now, you and animals have a body temperature that emits light in the infrared here. So in the visible, these animals are reflecting sunlight off of their surfaces. But if you have an infrared camera on the animals, you can see the difference between the warm-blooded animals and the cold-blooded animals. Or if a camera is on your face, you glow in the infrared. You're emitting radiative energy. It's a type of light here. Now, I'm sure you have your phone next to you like I do. I have my laptop, I have my Wi-Fi on, I just heated up some food. We have radio light, which is a type of radiative energy all around us because of the electronics that we use all the time. So they carry energy with you. So if you wanted to know, well, how does a cell phone create radio waves? Well, you know, it only works with a battery. So electrical potential energy can be supplied to electrons that move them, change it into kinetic energy. And when the electrons move, they produce radio signals, and that radio signal gets transferred to a cell tower, and then the cell tower could read it and send you signals back too. So there's lots of radio signals all around us, lots of radiative light. Okay, so these are different kinds of energy. We'll come back to this, different kind of energy. So now the question is, how can energy be transferred? Okay, well, we use the word heat a lot and temperature sometimes interchangeably. So I wanted to make another distinction about heat. So heat is the transfer of energy when we're talking about energy from a hotter object to a cooler object. Okay, so we've introduced temperature here, and we talked about energy. So here are just some 3 examples that I'll do talk about with everyday and how that can relate to something in astronomy. So heat here, again, is the transfer of energy, but there's different ways that the heat can be transported. And these mechanisms are conduction, convection, and radiation here. So I'm going to start with conduction first here. So let's talk about that warm coffee or warm tea, or warm beverage that you've had. You know that over time it'll cool off. So something's happening to allow the temperature of that liquid in your cup to go down over time. So remember, temperature is really kinetic energy. So if the temperature goes down, the motion of those molecules are going down, but the energy had to go somewhere. So where did the energy go? Okay, so it had to be transferred out. Okay, the heat here, the transfer energy. So if we take a microscopic look here, so what's really conduction? Conduction is when the molecules vibrate, okay, and they can transfer some of their kinetic energy to a nearby molecule. So in the case for the coffee mug, we have the liquid inside, and it's touching the inside walls of the ceramic mug, okay? And those particles bombard the ceramic mug, allowing some of the energy to be transferred to the edge of the mug. And then the mug molecules vibrate, okay, get warmer. You know that if you touch the outside. And then that can, the outside molecules, the air molecules can hit that mug, and some of that energy is transferred. So this is conduction of energy away from the inside of the coffee mug outwards, okay? Now, the molecules themselves in the coffee mug don't actually move away, unless we're talking about evaporation, and that's something else. Conduction here is also what's happening with the cast iron pot. The heat source is at the bottom, but you know that, for you cooks out there, you know that there's some material that conducts heat, gets hotter quicker, right? And sometimes it doesn't. So there's the heating of the metal, which can then conduct through the whole metal. So the sides of the pot or the pan here can get hot. Okay. The molecules don't actually move, though, in that cast iron pot. So what is an example of conduction of energy out by this idea of conduction? So if we look at Sirius, the brightest nighttime star in the sky, it actually has so Sirius this is the one that you would see with your actual eyes. There's a very faint companion next to it called Sirius B. It's a white dwarf star, which is a collapsed core of a dead star. So it's made out of really weird material that doesn't exist in that abundance on Earth, called degenerate gas, and we won't go into there. But what I want you to know about this is that it's extremely dense inside the white dwarf, and it's mostly made out of densely packed oxygen and carbon and electrons. The electrons are not attached to the carbon and the oxygen, but it's so dense that it acts like a crystalline structure, so very solid-like. And so the energy, the energy of those atoms in the interior of the white dwarf jostle around and conduct so that it can cool off. Now, eventually that hits an outer layer that won't act like a solid, acts more like a fluid. And then eventually at the surface, it emits light. And I'll talk about how radiative energy is another way to take energy away and cool it off. So at the surface of the star, it's not conducting, it's all in the interior here. So the analogy here is like passing a note from person to person to get it to the other side of the room. Okay, so the note is the energy, and you're passing it to one person, and the person passes it to the next person, to the next person, and that's conduction, because the energy is getting out, but the people are not moving. Now let's talk about convection here. So convection is when the particles physically can carry away the energy themselves. Okay, so in that note passing analogy, so instead of passing the note from person to person, you physically carry it to the other side of the room because you're the particle. And if you're moving it and carrying the note, the energy, you're the transporter of that energy here. So an example of this is when you're boiling water. So first, there's conduction going on with that heat source at the bottom of the glass, and the glass is absorbing that energy and heating up. So it's a solid, but it's heating up via conduction. But then the water sits on top of that, and there's some conduction here at the bottom as the water heats up. But then the water heats up, it gets a little bit less dense, and it starts to rise. And so those bubbles you see there are warmer water rising, okay, and physically taking that hotter material upwards. Now, where do we see this? We see this on the sun. So this is a image of the surface of the sun. It's roughly 11,800 by 6,700 miles view of the sun's surface. So this is just looking at the outermost layer of the star, of the sun. So what you see here in yellow is hotter gas. And what you see in black is the cooler gas that's sinking. So in the previous image, you saw the little bubbles of water going upwards. So imagine instead of water, a big bubble of hot gas going up to the surface. And you see this light, which is radiating away. So that's actually how it's cooling on the surface. But the heat in the inside of the sun is coming up by these convective cells. Now, these cells are pretty large. They're about the size of Texas. Okay, and this is a time-lapse image. You can see here, this was taken in 2019 over the course of about 15 minutes or so. So you can see that there's motion here. And you see that there's also light being emitted here. So convection cells, again, are bringing the hot plasma from below the surface upwards. Now, the interior of some really massive stars also has this type of convection going on to bring the energy from nuclear fusion out from the core upwards. And that's one way that energy is transported out from the interior of really massive stars. Now, the last we have is radiation. So radiation is a heat transport mechanism that transports the energy by the light particles themselves, by the light waves. So light we can talk about as a particle, and we call that a photon, or we can talk about the electromagnetic wave that carries energy, which is electric fields and magnetic fields, but it carries energy. Now, in this campfire, you see visible light. Okay, you see it with your eyes, the light photons coming out of that combustion mechanism there is going into your eyes, it's being absorbed, you see the light, okay? Now, it's also really warm, okay? And we know the infrared light is emitted because you, quote unquote, feel it when your skin absorbs that infrared energy. That's why it feels warm to you. That's one reason why it feels really warm, because the infrared light is being absorbed. Same thing is happening with a hot coffee mug. It's also radiating. You can't see it in the visible, but if you turn on infrared camera, it does radiate. And you can see that the inner pieces here in yellow is hotter. The ceramic mug is not as hot as the liquid, but it's definitely not as warm as the surrounding air here. So you can still feel that infrared radiation because it's being absorbed by your skin. So the analogy of radiation here is instead of passing the note or carrying the note yourself, you just throw the note. And the note is representing the photon moving through whatever substance it might be moving through. In this case, it's moving through the visible, and infrared light is moving through air. So we have lots of radiation examples in astronomy. Without radiation moving through space, we would not be able to capture the images that we do in astronomy. So again, the sun's surface is visible here in that image. We also see the cells in the convection zones bubbling upwards. The yellow is hotter than the dark cells of gas going down. So there's something with the temperature of the gas that makes the intensity of the light change, okay? The temperature of stars also changes the visible color that you might see. So hotter stars look actually very blue-white because of the radiation that it's emitting because of the temperature of the star as a whole. Cooler stars like M dwarf stars are quite cooler than the sun and emit a lot of light in the red part of the spectrum. So they overall look red. So that's the one thing in astronomy that you can say when you look up at the space is the color of the star will tell you the temperature of the star. The bluer, whiter the star, it's a hotter star, and the redder the star, it's much warmer as well. It's a way that you can cool the surface of the of stars. This way the energy is carried away. Now, energy is being produced inside a normal star like the sun, so that energy is being replenished. In a planetary nebula, the gas here is being heated up by the ultraviolet radiation of a white dwarf that's at the center of that planetary nebula. And over time, that nebula has to cool off and has a very hard time of cooling off. And so eventually it does and emits light, and these particular molecules give off the light. And in the Orion Nebula, the same is true. There are very complex molecules here that are emitting in the infrared. Some of the stars that you see in here, this is the surface of the star, which is cooler, and you can see it in the infrared. And you can also see the gas that's really hot and glowing in this multi-wavelength image of the Orion Nebula. So there are different ways for energy to get transported away from objects in space by radiation, by conduction, or convection. And there's different kinds of energy as well. So let's see here. And so the conclusion here of my talk, the world around you is beautiful. The world that you are in every day is beautiful. There are a lot of things in your everyday life that you understand and you can think about in different ways. And so now you can start thinking about the connections to astronomy. The telescope is our virtual starship. The light comes to us. Our telescopes can detect it. We can take images. We can take the light apart and understand more physics that's going on, understand the different types of energy related to atoms and how we can see specific wavelengths of light and what energy conditions and temperature conditions and density conditions are needed for that to happen. We can see things moving through space, how quickly it moves through space. If it's hitting and shocking other material, it tells us so much about what's going on. And then once you figure that all out using your arsenal of information from your everyday experiences, you can sit down with your friends and family and talk about everything astronomy for as long as you want. So thank you so much.
Thank you, Quyen. I think that this sort of expresses kind of the fascination with astronomy that I've sort of had all my life, is that you learn physics and you learn about all these cool things. But the reason to go into astrophysics is because then you get to apply all these physical principles to that cool stuff out there, you know? And to me, it's like it's problem solving on the grandest scale, right?
Mm-hmm.
And you get all these ideas, and then you can say, all right, well, that thing is 20 million light years away, but using what I know here, I can figure out what's going on out there.
Mm-hmm.
And I've always thought that just really cool.
It is. And I think in some ways, it sometimes our job is a little bit more simple in some ways, because we have to use the tools of the things that we know here to be able to interpret what's going on out there, because we can never go there and get that sample. There's very limited examples of return samples in astronomy, more in planetary science, of course. But so that puzzle piece is absolutely very true for many astronomers. And our tools are physics, forces, and energy.
Yes.
And interaction of light with particles.
And you know, I sort of think of it as it's a detective novel type thing, where you just get this, you get the clues from the light that you receive from these distant objects, and then you get to try and puzzle out what's going on.
Mm-hmm. Yeah, one of my most I like to tell people when I'm at this is in pre-pandemic days, having people at the telescope and just, you know, when they see pictures and they say that can't be real, that can't be Saturn, that can't be Jupiter, that's a picture you put at the end. I'm like, no, it's really, you know, it's really what you're seeing, or those stars. And so the piece of wonder that I always like people to walk away with is when you're looking out in space, that light came from something in space. okay, whether it's reflected or actually emitted. And that light went through the Earth's atmosphere, went through the telescope, got focused by the telescope, but then it went into your eye, and then it has to interact with your eye to actually see it. And so that's one way of you interacting with the universe, because that's light that you're receiving. Now, if it's infrared light, there's another way you can think about it. You can think about infrared light could warm things up. So there could be also an example where we have an infrared telescope or even sub-millimeter telescope where the heat is actually what is being detected. So it's another way that you can think about interacting with the universe.
Okay, well, we've had a good discussion on the YouTube chat. And Grant is going to come join us and I'm sure he's found several questions from there. And if he hasn't, I noted a couple to myself.
Yeah, I
Awesome.
grabbed a few. First off, before we begin the question and answer section, Frank, we need you to turn yourself up a little bit or move the mic closer, if you would.
Closer.
Yes.
It sounds really good in my feedback.
I believe you, but on YouTube it's a little different. All right. So first off, I want to throw this in there because you both already knew this was coming. Where do gravitational waves fit into your energy theory?
Well, gravitational waves. Let me think about that one for a second. I have to say that I'm not an expert on gravitational waves, and I might have to come back to that question.
Okay, no, that's fair.
I'll bat it over to Frank's arena.
All right, so I think of gravitational waves as motion of space-time itself, right? So I would think of it as more of a conduction of the ripples passing through space-time, right? Because when we detect a gravitational wave, what we're actually detecting is a stretching of space. Right, we've got these two laser interferometers that are looking off in parallel directions, and they're measuring the distance here versus the distance here, and we're actually seeing a tiny, 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 tiny stretch of space-time. So to me, that sort of makes it into conduction, but of space-time itself, which is really kind of crazy.
Well, what I'll throw in there is thinking about distance and speed, right? So that stretching of space means that the length that has to be traveled is slightly different. And so these mirrors on LIGO are quite sensitive that it could really measure the time delay, or it actually is these waves meeting up. And if they meet up right at the same time, you don't get these shadows. But if they meet up just slightly off because the space has been distorted, you're going to see what are called interference fringes. It's a way that the light waves don't match up. And so in some ways, you can think about it as a distance and time measurement with those arms that Frank was just talking about.
What do we got next?
So next one. Is the point of rotation for the Milky Way equivalent to its center of mass? If it's not, would you expand a little more on how we actually move within our galaxy?
Okay, so one thing that I didn't go into is how the stars in the Milky Way actually move around the center of the Milky Way. A lot of mass exists at the center of the Milky Way in the supermassive black hole that's at the center, which is about 4 million times the mass of the sun. But it's not the bulk of the mass. There's over 100 billion stars, plus dust and gas in the Milky Way. So for the most part, objects do orbit around the center of the galaxy, but not like a solid merry-go-round that you were seeing in the images before. So in a merry-go-round, if you're in the inside of the merry-go-round, you still go around the center in the same amount of time if you're in the outside of the merry-go-round. And that's not true for the Milky Way. We call that the carousel a solid body rotation around the center of the carousel. And in the Milky Way, that's not true. And this is actually how dark matter was discovered, was that it turns out that there's as much mass inside the orbit of the sun from all the stars combined as there is outside. And because of that, the motion of stars in circular orbits, if we make that rough approximation, would not be the same as the type of physics that dictates how planets go around the sun. So there's a law called Kepler's laws for planetary motion that can very well, very accurately tell you the orbit of a planet going around the sun, where the sun has the majority of the mass in the solar system. And Kepler lived in the 1700s and was able to figure this out. This is how astronomers today look at how planets go around other stars and looking at those exoplanets. But the physics there, that's different. That's a concentration of mass at the center in those star systems with planets, whereas the stars in the Milky Way are not concentrated in that way. And so, so we can talk about the sun's rotation at its particular point in its particular location around the Milky Way. And we can also do that for other stars. And knowing the motions of the stars everywhere in the galaxy lets us understand how the galaxy was put together. So you can see if was there interactions in the past. So looking at the positions of stars, you might see, oh, there's a tidal tail of stars that looks really weird. Could that have been a gravitational interaction with a satellite galaxy that's off over here? And so just those motions alone tells us a lot, but we always start in one assumption until the assumptions break down. And then we start to bring in more complicated motions to explain it, with gravitational forces being the main driver of those motions.
All right, great. What's
next? All right. Frank, if you've got one, I'm reading through a couple more.
Okay. I noted one that came up immediately when you were talking about parallax. They wanted to know the sun is also moving. So doesn't that change the parallax?
Over the course of 6 months, let me think about that. Does it change the parallax? If it does, it's quite minor in comparison to the motion that you see to the Earth going around the sun over the course of 6 months here.
Right. And
the positions of some of the, go ahead.
Oh, I was just going to say, related question. When you showed that Gaia movie and there were the constellations changing, what was the time scale? Is that 10,000 years, that 100,000, a million years?
I do not know, but I will drop I don't know, I guess I can pass the link to Grant and to connect people to the information. I'm sorry.
I can throw it up in the chat. It's
okay, thanks. Yeah.
Well, I know it can't be like 1,000 years, right? Because, you know, we've tracked the constellations for 1,000 years and they move a little bit, but they don't move that much. So I was guessing it had to be at least 100,000 years, maybe a million years for the constellations to move as much as it was shown in that Gaia video.
Gotcha. I actually have a really good one. I like this. I like this a lot. So, what are some of the best introductory materials or like books or research on the topic that you would recommend to somebody who's just starting off?
These are my personal recommendations.
Yes.
No endorsement from Space Telescope at all.
On my own.
Yes. I really enjoy the Crash Course Astronomy by Phil Plait. I think that's how you say his last name. They're nice and short. They do a lot of really great analogies to help you understand astronomy. Let's see, what else? Let me think some more. Frank, do you have some suggestions?
No, I don't have off the top of my head suggestions. There are a tremendous number of materials that I might have on my bookshelf or other places, but I don't. I haven't kept that sort of thing off the top of my head.
I've got one that I can remember. It's an author, not a book, but Michio Kaku is very good at explaining very dense physics theory in a way that makes sense. Because I am not an astronomer, as you guys are. So if I can get it, it's a decent resource for the chat.
Well, one of the things I will supply, well, this is also disclaimer, I work on a lot of NASA's Universal Learning materials. And so we do create a whole bunch of products for ViewSpace, which people might not be familiar with. A lot of museums use it. So sometimes when you are at a planetarium, you might see videos outside while you're waiting. Most likely that's ViewSpace. But we also create these great interactives where you can look at the universe in different wavelengths, for example, like the Eagle Nebula, and you could slide the bar around to see the universe in X-rays and radio. And there's a description of the science below that, as well as additional resources. So for someone who's just starting and trying to get a little idea that is really a novice, I guess that's one way to say it. That's a great place to start. And we have a lot of material from exoplanets, star forming regions, star formation, different kinds of stars, stellar death there. So that's also a really great place to start. And I personally love to read articles written for the general public. So scouring the different, New York Times has great articles that are written. Forbes has one by Ethan Siegel, which I really enjoy.
And it's important not to forget about our websites too, like Hubble site, and James Webb and STSCI, like all of, at least information about the telescopes and their function. There's a lot on there, and it is presented in a way that you can understand if you are not a fellow astronomer.
Definitely.
Okay, so we had an interesting question that was directly relevant to your talk. You mentioned absolute zero as a limit on how cold things could be. Is there a limit on how hot things can be?
Oh, is there a limit that can be? I guess, let's see. I never taught that in my class. From a star standpoint, there is a limit to how massive a star can be, because it would generate so much energy, it would just blow itself apart. So so if we're just talking about stars being stable and not creating so much radiation, because there's a point where if there's so much light being produced, it actually can create a force like a pressure and push the star outwards and actually destroy it. So I will say that there's definitely a limit related to how much radiation can be produced in really massive stars, which is connected to how hot the interior is. That number I do not know off the top of my head. Now, if we talk about the early universe right after the Big Bang, I believe there are temperatures associated with the very early universe as particles are created. Now, remember, E equals mc squared, right? So mass has energy. So in the early universe, it was all energy. But as the universe cooled off, so that's another way you can think of an infinite temperature, but then the universe is expanding in all directions, or expanding and cooling off over time. And as it cools off, then that energy can be converted into mass of these particles. And as the universe cooled off, it can cool off in a certain amount of time, and it creates particles in certain abundances. So there's a reason why the hydrogen and helium abundance in the universe is the way it is, because the universe cooled off in a very specific way. So going back to the original question of, is there a temperature limit, the high end, then if we go back to the early times in the universe, then it's very, very high.
Yeah, I don't know what the temperature was at Planck time. But, I mean, in astronomy, we study temperatures of, thousands of degrees for stars, and, 100,000 and millions of degrees for X-ray. And the cores of stars are at millions of degrees, or the cores of red giant stars and the stuff are at hundreds of millions of degrees, et cetera. You have to go to particle physics really to get the super high temperatures. And I'm not an expert in particle physics, so I'm not going to go there. But
No.
That's one of the difficult things about these talks, is we have such incredibly specific areas of expertise each talk.
Yeah.
It's nice to have general information like this for everybody to get the basis to understand some of the more higher level.
Yeah, I'll have to start making my list of questions with the answers after this talk and have it be like, let me look at my sheet, everyone.
All right, so
you got Grant.
We're looking pretty good. Oh, this is a term that I've never heard before. Paleoastronomy.
Ooh, paleo. It might be, is it similar to archaeoastronomy?
That's a great question. I've just never
Oh,
seen the term before.
well, that's a different one. I'm going to take a stab at this. So when we think of paleontology and studying things on Earth and looking at things in the past to reconstruct the history of the Earth at different eras, okay, we're trying to use that information to say how it got built up to what we see today. So if you think about that in astronomy, what we see is the leftovers of any event that might have happened in the past. So hydrogen and helium is a signature of the Big Bang and the universe cooling. So we can use that to figure out what happened in the past and leading up to today, because we know most of the elements that are more massive than helium were all created in the inside of stars, okay, because of the way we know the abundances. So that's just going back to that detective language that Frank was talking about. We have the information, and we have to try to build up the scenario to get it to where we see it today. Okay, so for looking at the Milky Way galaxy, we see distributions of stars that are there's older stars that are in the center regions. There are younger stars in the arms, and there are these halo stars and globular clusters that are kind of spread out above and below the disk that are really old. So if you just took a look at the ages of stars in our galaxy and they were in different places, that gives you an idea of when they might have formed first. So the halo stars and the globular cluster stars turn out to be some of the oldest stars in the universe in our galaxy. And so they must have formed first, whereas the stars in the disk form later. So the evolution of the Milky Way we can start to understand it by seeing what stars are there, how old they are, where they are, and how they're moving. Okay, so and so that's kind of that. I'm guessing that's where that person's paleoastronomy might have come from. I think that's the Frank. Have you heard that term before? But that's my guess, my interpretation.
I just looked it up on Wiktionary, and it says the relationship of information about the sky to historical records, a fusion discipline between paleontology and astronomy.
So I usually interpret what that definition that you just said, Frank, is archaeoastronomy. So there's a lot of archaeoastronomy.
Google takes it and immediately turns it into archaeoastronomy if you search for paleoastronomy. But
that makes sense.
Actually has this.
Well, what I just described, my version of paleoastronomy is looking at the history on billions of years time scale to get to where we see today. Archaeoastronomy is quite interesting as well. And by the way, on VSpace, there's 2 new videos that talk about archaeoastronomy and looking at the night sky that the Maya saw, and as well as over time, how many supernova explosions have you seen with just your eyes? Make a guess and then go see the video.
All right.
Okay,
so
Frank, do we have one more question for her?
Yeah, I'll finish it out with this last question, kind of related to the previous about the maximum temperature and what have you. So by logical deduction, would the center of galaxies then be the hottest places in the observable universe as we know it?
No, it would not. That's a great, I could see the analogy thinking of collections of, the galaxy is definitely a collection of billions of stars, but in reality, the space between the stars is quite large. There's a lot of dust and gas, but the chances of another star hitting us, the sun and the solar system, is very, very, very low. Not something you should worry about. But it's not a solid object like a star is. A star is really dense, and because of the gravity of the gas pushing down on the core, that's actually why the core of a star is so hot, is because it's the molecules are moving around so fast as it's being pushed down by the weight of all the overlaying materials. So for those of you who are interested, look at something called gravitational equilibrium. It's the way the inside of a star has its temperature and pressure and density at a very specific way that's outlined by some really simple physics, actually 6 equations to be exact, I think 6 or 7. but the inside of a star is hot because of that. That's not the same scenario in a galaxy because the stars are not all pushing on each other like the density of a star. So it's not quite the same. The centers of, let's see, let me think of some other centers that might be really hot. Star centers, very, very much so. Even the cores of white dwarfs and neutron stars would be hot as a result of that gravity, the weight of material on top of it as well.
Okay.
Okay.
Well, thank you very much, Quinn. I think we have taxed your brain and going many different directions.
Thank you, everyone, for that. Taxing my brain is great.
As you have taxed their brains into thinking about what they see around them and how it applies to the universe. Next month on August 3rd, the importance of small objects, exocomets. That's a really cool idea. We will see you then. Thank you all for coming and have a great day. Have a great